So let's continue. There we have that one. Good. So the next thing is another way of looking at the data through some statistical tools. And in the math classes, you have covered probably linear algebra and also some statistics. And these two, linking those two together, gives you a very powerful tool. And it's called principal component analysis. You do, in principle, eigenvalue decomposition of the covariance matrix of the data. And in this case, we're talking about the covariance matrix between different observations. So it could be some spectral information. And yeah, I said already, we compute the covariance or correlation matrix. That we do a decomposition, and then we look at the singular values from the decomposition, and we use the eigenvectors for transformation of the data. May sound a bit abstract to begin with, but let's look at an example. We have some, this is actually fake spectroscopy data, and from the data we have some noise as a baseline. We have some spectrum for fat, which has one bump here and a clear peak. And then we have some. And if you have a large amount of these data sets and want to detect which is and which is protein, it's not very obvious looking at a lot of these curves. So what we can do is now to take a load of data and looking into which kind of cells are more fat-like and more protein-like. And at the first look, we have several curves, several measurements, overloading them on each other. Yeah, here we look just at two curves, curve 1 and 2, do a plot together, and it doesn't make much. And you want pattern analysis on these. And here now we come to the principal component analysis, where we fit the data. So we have our test data. We say we want to compute 5 principal components. It would be, in principle, that we look at the eigenvectors for the first 5 singular values. And do a fit on it. PCA is a part of scikit-learn. And in the decomposition segment. And now if we look at the transformed data, clear groups, and these groups are very easy to find, k-means or something. And looking at the components individually, so these would be the principal component plots. You can see that there is also a clear distinction between the 3 different data sets. So this is a nice way of identifying where you have the right data, the different classes. Of course, you have to tell what of these classes are, but I think with some reference, you can pretty quick identify what is what. And looking at the singular values, we can see also which of the components are most important. And that's pretty clear if we look at this bar chart. The first 2 components actually contain most of the information in this decomposition, while the other 3 essentially nothing. And that also gives us a very good way of compressing our data from having groups. And that is making life easier also when you try to do the segmentation later. And the example, a real example, is principal component in material science. And want to look at crystal textures and in some metals. I think it was some kind of iron iron samples used in different ways. And the method was based on Bragg edge imaging, which goes down to diffraction behavior that we observe with in the intensity. And depending on the lattice spacing, you get different. And if you look at different wavelengths. And now we have an example where you look at the cubic ion, gives you a spectrum like this. And depending on the crystal alignment in the sample, you get a very characteristic kind of plot here. And you can see that you have, that one. Different kinds of ion give you different responses. So these two are actually two types of ion, and you see pretty clearly that they have different responses. So, looking now at some data, we have a couple of samples, and the average intensity is not very exciting. You can not see very much. The bright here is actually just the tape that was used to glue together. And if we look at the single wavelengths, about the same behavior, but a bit noisier because we have less neutrons available. And we have, in principle here, 3 different groups. We have just air around the object. We have some material, which gives us this edgy peak that we were looking at. And we also have the spacers or the tape that was used. Now, this doesn't give us much way of determining the difference between the samples, but through the principal component analysis, we need to do a couple of steps that brings us, first we need to prepare the data and subtract this mean and standard deviation, do some normalization before we can put it into the analysis. And then again, we do principal component analysis with the PCA5 elements, and we do the fitting on that. The outcome is now that we have the eigenvalues here that actually up to 3 eigenvalues are relatively relevant, but then it flattens out. And now looking at the eigenvectors, they look quite weird, but we see now that we have a little bit different information in them. An important thing to say about principal component analysis, it's a pure statistical method, and the eigenvectors are not physical. So it's just a linear combination of different informations. And so you can't use it for a direct physical interpretation, but it can help you to do the segmentation. Looking at component 1 versus component 2, you get this distribution. You can see you have some kind of triangle here, but it's with this kind of plot, it's not so easy to really see what's going on. So let's go for the next one, is that we put just a different transparency on the dots. And if we set the alpha parameter in the plot to 0.05, you can really see that you have a clear cluster up in this corner. You have 1, maybe 2 clusters here, and you have 2 clear clusters around here. And that can help now to do some segmentation on this data if you want to go on with that. And this is also something you can use when you want to visualize the data. And now I'm doing color coding using the 3 first principal components as RGB. And the image objects, and in the middle you have something else. And this was actually what my colleagues wanted to see with this these samples because they did it with some kind of additive manufacturing method, and they wanted to know what is the surface treatment doing to these objects. So this actually helped to identify the items that were different from others. Yeah, and then we can use these two in combination and also to distinguish a little bit better what we are doing. And yeah, of the principal component analysis is that we can compute it because the eigenvectors actually can be interpreted as some kind of rotation matrix, in particular if you have three components. And that can help us looking at the covariance matrix again, doing the eigenvalue decomposition, and these now actually can be interpreted as rotation matrices. And if we look at this, I think it's a blob from the car. Yeah, that's one of the cars. And we see that it has some kind of orientation in our image. And by computing the eigenvectors, you can see that you have two orientations within the object. And these principal orientations we can use now to rotate the sample so that it's aligned as much as possible to the main axis of the plot. And this is the rotation then, and you can see that it's probably fitting in the box the best way. But what you also can use it for is to see, looking at average orientations within these objects. So if you have many objects that are in some way and have orientations, you can get information about how they are rotated. Yeah, so you can use the principal component for a couple of different applications. So often it is to reduce the data and making it easier to interpret, but you can also have this geometric principle to observe how things are rotated. And the elliptical model, yeah. So you can also see if it's an ellipsoid by looking at the length of these principal components. And that's also a way to bring more information, for example, into the properties of the objects. And that was next time. It's not next time. Well, we will look at some different things further on objects next time too. But actually, what I want to do now is to switch to, this one. And the next part is now about, come on. Shape and texture. And what we can do with these objects or images that we have labeled, we can look into more about distances in them and also getting metrics based on the distances. And again, there is quite a lot of literature on that. And yeah, the main things we are looking into now are the distance map, which is related to actually the thickness map, and then we can look at some characteristic shapes, and I'm rounding off with texture analysis. And we have already looked at many types of objects and what we can measure from them, but now we want to look also at, for example, patterns. If you have objects and you want to distinguish them, the only way to distinguish them is actually what kind of pattern they represent. Or looking at areas, if you look at a satellite photo from a landscape, with the help of patterns, you can identify if you have forest, if you have agricultural land, or if you have habitated areas. Again, we need some modules, and now we come to the distance map. So a distance map is a transform of the image into looking at the distance from shapes in the object and see how far away from the shape you are. And that can be done with different metrics. Have the Euclidean distance, and you can also look at the city block or checker board, which is also 4 connected or 8 connected, or according to the manual before I saw, you can also call it for 1 and 2 connected. So popular now 4 connected and 8 connected. Looking at the distance map, we have this object. It's essentially just a circle. And the Euclidean distance map looks where we look at the distance from the surface inwards into the object. And if you look at these values, you can see that this 2 comes that we have 1, 2 pixels coming in. Here on the boundary, we have the blue ones, which are 1, and the green ones here are 1.4, which is actually the square root of 2. So there is only the only way to get in here is through the diagonal. And of course, then you have some interesting combinations here. So you get square root of 5, square root of 6, etc. to get to these positions. And if we look at different kinds of metrics, you can see these are very small numbers, so you probably have to see it on your own screen. But so we have different distance metrics give us also different distance maps. And why is that interesting? I mean, the Euclidean is, say, the exact one, but why would we need something like this? That is the question now. So we have here, well, that's just the manual for the distance. Now we come to the point why you would be interested in doing different metrics. And let's say we have these large images and we want to compute the distance transform. It's a lot of neighborhood calculations, it's a lot of square roots, and all that costs time. Looking at these is the EDT from SciPy, and that apparently takes 15 milliseconds, which for the large image would correspond to 20 minutes. No, a quarter of an hour. It's 0.23. So then we have the brute force algorithm, something that we did ourselves maybe. And then it takes 400 milliseconds. And if you upscale that to the large tomography image, it would be 6 hours instead of 15 minutes. And if you would take the city block type, then you don't do all the square roots. And with that, you can do further speed up, actually down to 0.04 hours. So that is where it matters. So if you can survive with the precision you get from this kind of analysis, then and are also required to do a lot of processing, then it may be a good idea. The brute force you can forget because it's anyway too slow. And this one would be, so the choice would be between these two, depending on what precision you need. Some cases you really need the precision of the Euclidean, then the choice is given. But in other cases, if you just want to do it as some kind of pre-calculation for the next step, then that one may be a relevant choice. And well, Here is also the algorithm for computing the brute force. And as you can see, we have, in principle, again, 4 loops, 2 to scan the image and 2 to look into the neighborhood. And this is also an because we compute the square roots in here. And here we have our test image to play with, and looking at the simulation. I hope that would be running, but it isn't. Whoops. No. I need to skip that one. Yeah. What you would see is more or less how the distance field is moving in. Apparently, I lost the notebook I started up before, so probably I closed the window. So that is not working. So let's skip that. And then we have different types. So here would be the city block type, where you only compute the absolute distance, and that is of course much faster than doing the Euclidean. And that is the same simulation. Then is one thing that is important to think about when you work with the distance map. The algorithms usually assume that you have isotropic voxels. But if you, for example, would do take some medical imaging tomography, then you have as one parameter how thick slices you want. And that would give you anisotropic voxels. So you have the pixel size, so to say, which gives you 2 dimensions, and then you have the slice thickness, and that will be a problem. Rewrite your code a little bit to handle that kind of problems. And what does it show? We can have in the original definition, we have what we need is a foreground to background, or we can also do a background to foreground distance. And in the foreground to background, you do. Isn't that flipped? It is. Okay. I think I flipped the labels here. So here we go from the background into the foreground. So these are flipped. Sorry about that. But anyway, you can see that with this object, we have distance field, and if you go from the object out in the background, then you can have a very large distance field. And this can look very differently. Let's see. Oh, no, come on. I need to run this. Excuse me. I think I need to go back here. So there it is. And the rest I can do. Yeah. So here we have 2 objects, and we look at the average distances within the objects, and depending on how these objects they grow, that we need to start again. How these objects grow. So we have 2 disks that are increasing the diameter, and at some point they actually grow together, and then we have, instead of just 1 object, 2 objects, we have a single object, and that is what you see here. And the average area is changing, but the distance is still quite constant. So we can use the distance as a way of measuring object sizes instead of using the area, and that can be quite useful. And looking at some real images, we have these cell images. What we can do here, we have the mask, And now we measure the foreground measurement, where we can see we have some characteristic radii within these objects. And if we look at the distance map of the background instead, we can actually measure the average between objects instead, and getting distributions about how distant are they from each other. And that can be used if you look at, for example, histograms of this one. You can determine if you have in different regions have closer clusters of objects or more remote clusters of objects. We can also look at the cortex mask that we had before, seeing that we have more or less a very narrow object, and then you can combine it also, for example, the maximum distance along the ridge, compare that to the area, and then you can get some kind of sphericity metric, if you like that. And here you can see the histogram that the very long distances are very few, so we can see that it is mainly distributed on a narrow plane, and then there is some thicker place which gives you this these large values in the end, and those would be these down here. Then I have, that's the question if I, yeah, I do that one. It's a little demo I have working with isoline averages, and this is like a little bit more like a workshop thing. So we have a task that we want to compute. Hello. We want to compute the average intensity in this area. So it's some kind of clay material, and they want to know the waterfront, how it goes into this material. And this we want to do as a profile from the surface into the material. But here you can see we have a lot of different obstacles. One is we have a mask around here, which gives us a round image. And that is something we need to get rid of. And to compute this profile, we need to have a distance map, which gives us then isolines where we can compute the average value at each distance. So the first thing I needed to do was to create a mask to sort out what is background, or definitely unneeded background, and my interested field. Then I put a threshold in order to find the edge line here. That I did using some of the automatic algorithms. I think it was the minimum between the peaks. And then I get a thresholded image, and as you can see, I have some misclassified pixels here. And if you remember what to do when we have misclassified pixels, there are different ways. We could try doing some filtering to get a better signal to noise ratio, and thereby get a more clearer choice where we put the threshold. In this case, I chose to do just morphological opening and closing to get rid of these spots, and then I get a clean image, but still I have this background up here. So I do some cropping in order to handle that problem. So because if I keep it here and compute the distance map, then I also actually have distances that go out in the really don't care region. So I need to cut that piece. So I do some cropping, and then I come to these images, and then we put everything together to do the whole analysis. I needed also to have a don't touch region down here, because that's also outside. And now I want to compute this isoline statistics. And again, let's see, I use, as earlier this morning, use this unique to compute, to find out where I had, which actual distances I have in this map. And then I compute, for every distance, I compute the average, I compute standard deviation, and finally, we can do a plot, something like this. And that would be the end product of this investigation, where we have distance from the surface along this axis. If I wanted metric, I would have to multiply it by the pixel size. And then we have the average intensity as a trend line. And outside we have 1.6 times the standard deviation to see where we have the values. So this is from a user. I helped to get the things right. And let's see, do I have another one? No, that's gone. Okay, I have another example where we looked at the water content in the near area around roots, but that one is was lost when I closed the wrong window. So that was just a little workflow, and you see there are many steps to be done to do. And this is not in the same folder as today's lecture, but there is in the lecture main folder, there is an isoline average if you want to look into this example in more detail if you need that. So let's go back to this one. The thickness map is almost a distance map, but not. So if you look at this, you have the distance map of, in this case, it was just a bundle of spheres. And if you measure the distance map between them, you can see that you have distances that are going out from the object. And in the middle, the furthest point from the objects, you have the maximum. This is not so relevant for many physical investigations, but instead you want to look at the pore size, and that is the same as the largest sphere or disk that you can print in the area between the foreground pixels is that radius is plotted all over the this area. And then you can see what it looks like, that we have a very large pore here, and that actually touches until the grain. And the closer you get, and also in the throats, you get different values. And that is something that is used in porous media research a lot, when you want to to predict what kind of water flow you can have and water retention you can have in your porous samples. And here were some applications exactly from this, where you can look at how the diffusion through these. So this was a simulations experiments based on different packings, and you can see how they behave. Thickness map can be also implemented. It's a bit messier to do because you always have to in-paint a lot of large disks or spheres. So it's a bit more time consuming than computing the distance map. And here you have some examples, again on the cell image, where you can see how we have some large objects here. And it can actually also give you more idea about the size of the objects that we have, instead of just computing the area of it. And then we can see the distances between the objects in nice color code. And so these are ways that an alternative to using the distance transform. And we can see here the distribution, that we have some large objects, some pixels in large objects, and we have some pixels in small objects. And the average background is apparently the average pore size is around 60 pixels distance. In 3D, we can also compute the distance maps, and that's no problem. The definition is easy to upgrade to more dimensions, so that's nothing too much to worry about. So here we have a stack of images through an object and we want to do these measurements in the images, and that's just adding one dimension to the equations, adding some more loops to check the image and the neighborhood. And here we have an example of that. It was actually created as some mesh. Let's see, where am I? Here. Can I? No, I can't. Okay, but anyway, here is a mesh of this object that can be looked at, and then we can take this mesh. It was some kind of triangulation, looking at the area. And I think I have skipped out some slides here because the idea was I should talk about Martian cubes here, which is an algorithm that can identify where you have the surface. And the algorithm is going through the image, looking at the neighborhood for different constellations of black and white, and from that it can get the nodes and the vertices from the edges and the vertices from triangles that describe the surface. And and here we have the distance transform from this object in different directions. So here we have axial slices and sagittal slices. You can see that you have elongated bubbles in this data set already from this direct view. And then we can also compute some thickness map in the bubbles. And it's in principle. Hello. And there's just some sorting around the bubbles. We found 98 bubbles, and looking at the bubble projection, so we're just projecting all the bubbles in the different directions, we can see how they are distributed within the material. And here are some slices showing the same thing, where we have our bubbles, and the color coding is the size of the bubbles. And then we can also find some interfaces and surfaces between the objects, and I think, surface area is one thing, perimeter, and then we can look at meshes on how the different objects are organized and what they look for. And these meshes, they are used mainly, very often as a part of the visualization. So if you hear about something called isosurface rendering, they need usually in the computer graphics, they need these meshes. But another option when you look at these is to use it in finite element modeling, where you can put the strain relations, stress-strain relations on each point and do numerical calculations on these objects to, for example, verify what is happening under different conditions in under loading conditions when you do an imaging experiment. And here we come to the Martian cubes. That was it. Okay. Another thing is that the reason why we want to have these triangle meshes is that, as you saw before, we have it's very hard to describe with voxels a perfect shape. And with the help of meshes, we can go actually to sub-pixel precision and define the surface much more precise. And that is what is done with using this Martian cube. And it's mostly done using into 3D, using a 2x2x2 neighborhood. And that gives us a lookup table that tells us which kind of triangle we should use to identify this area. And the refined version of Martian cube is that you actually look at the 4 points and try to find exactly where you should put the triangle within it. And there are a couple of nice videos showing how it works. If you are into working with Martian cubes and looking more into it. And from these, you can actually also compute local curvature. You can, in principle, compute that one too. by doing some derivative computations locally in the images. And you can see here the relations you can compute, that low curvature means you have a large radius in the area. And from that, you can actually use it for one thing in what's it called? Lightning conditions to get the right light from images when you do the rendering. But you can also use it for some filtering techniques. Some filters actually are based on using the curvature to guide how to run the filtering effect. For example, the ISS filter that I mentioned during the filter lecture is actually using the local curvatures to compute this. Can also be used in physical analysis, looking at the shapes or what happens in the image, how does the curvature change in the object. And we can look at surface normals. That's mainly also used for the visualization visualization purpose. And you can get these hedgehog visualizations if you like. So I think I need to skip. Oh yes, I need to skip on a bit here now. Sorry for that. I'm lost in time today. So I want to give the last minutes on texture analysis. And texture is that, well, our world is full of patterns. Everywhere we have patterns, and those patterns can be used to identify different things. So here I just give some examples. We have some leaves. We have looking at some grains on the cornfield. We have a forest. That actually I can't see what it is. Some cracked soil, a brick and a stone wall, water, fireworks, and so on. Also fingerprints could be looked at it. And to analyze this, we can use some so-called texture features that analyze local frequencies in principle within the images. And here we have some basic textures. We have one that is lined up in the vertical direction, one is lined up with horizontal lines, and here we have some blobs. And I think there should be, no, that was all. And here we can look at occurrence matrix, and in principle, it's looking at the distance, at different distances, it's looking at the gray levels that occur. And then from that, we can get histograms at different distances, and that gives us this kind of representation. And that is actually a 4D representation, so it's not so easy to grasp directly. But if we look at this image, we are producing some co-occurrence matrices and for the different patterns. So you can really see that depending on what kind of pattern we have, you get different kinds of co-occurrence matrices. And this matrix can be both on distance and orientation. So you can, when you call for this co-occurrence matrix, you can actually get it, you can determine if you want which distances you want to use and which orientations you want to analyze. This can also be done using correlation, looking at local correlations within the image, what kind of, and from those you can also learn a bit about how the textures look like. And again, we can look at here. We have some orientations. I can't go up. Okay. And yeah, anyway, you can see in this how the distance co-occurrence behaves depending on which distances you're looking at. And then you can get, sometimes you get oscillations, sometimes you don't. Depends a little bit on how complex the pattern is. Oh, that one wasn't hidden. I want to hide it. That's better. So we have an example here. It's from a sea urchin, the skeleton, a microscope image of its skeleton. And you can see in this image that we have a very porous material, but you can also maybe see that we have different regions with different distances and more or less material, and also different intensities. And this example is something I, with my layman eye, was labeling up, that we have different regions. I found out that we have, in principle, these 5 regions. The outer perimeter, and then there is a transition zone, then there is a closure zone, and in the end, this part I think is just a perspective distortion actually from the microscope. But anyway, it has a different texture. And now I want to try to analyze this using texture analysis and the co-occurrence. And the algorithm, or the workflow we have for this is, in principle, first we load some images. And to get the texture statistics, we have to reduce the image into tiles that we work on. Then we can compute some features, vectors. Here I use the collocation matrix and collocation properties. But you could maybe also use something else. Depends on what you want to look at. Could be, for example, local gradients or sum of the gradient, or something like that. And then from these properties, we get some histograms. And from the histograms, in principle, we should be able to do clustering. And again, it's not hidden. Okay. I think I switched to, to doing it like this. So the first step is that we do, just make it larger. So first we do the tiling. So we divide the image into small groups of sub-images that we are going to compute our statistics on. And then we compute different gray level collocation properties. And this collocation matrix has these different metrics that we can do. Energy is essentially the square root of this one, so I actually skip it. It doesn't make sense when we look at the curves afterwards. And then we compute the feature vectors of the data. That gives us quite a lot of code for the initialization. First, we looked here at some property images. And for the initialization, we also want a list for handling these. And then for each patch in our object, we compute the gray collocation matrix, some scores, and finally we print the results, or put the results back into the image. The resulting images from this is that we have these are the pre-provided images. So this was the original. Here are the labeled masks reduced by the tiles that we had. And then we get some contrast image, dissimilarity image, homogeneity, correlation, and ASM. And you can see that there is somewhere here a trend that should more or less identify these regions. And now would be the next step, finding a way how we can cluster this. I tried using k-means, but to be honest, it didn't turn out pretty well. But here we can also look at some statistics around it using the data frame describe. And another way we can also look at it visually. And here you have the pair plot that is provided by Seaborn, where you look at the different component pairwise, and in the diagonal you have the histograms for each class. And the color coding is given by the classes I labeled up in my example. And well, it doesn't look so easy because there is a large overlap, and also if you look at the original image, they are quite close, in particular in the main area, in the larger part of the image. So if we just take a close, no, wait. Ah, come on. Okay, I need to upload that part. Apparently I did it on another computer and it didn't come in here. Okay. So anyway, what I wanted to look at was, in principle, looking at the average intensity and the intensity standard deviation, and we can identify that we have two main clusters here and here, and those clusters are more or less corresponding to this area and this area. So they are easy to distinguish here. And the other areas, yeah, maybe I did the labeling not ideally, but the other areas, they are quite much overlapping, so they are not so easy to identify. I'm sorry for not having that part around, but yeah. And then we can just skip on to the summary and call it a day. So what we talked about today was labeling. Now in this part, it was actually more about distance maps and how to visualize 3D data and doing some surface descriptions. There I actually skipped on quite much, but the main idea here was we can look at the curvature of different surfaces and describe properties based on that. Finally, now I looked at the texture analysis, where we looked at the co-location matrix. You can also do correlation, local correlation, and another thing you could look into would be different filterings, so taking different high-pass filters, seeing which frequency components you have in the images, and so texture analysis is also a great field within machine learning, where that are probably in many cases better at finding these regions. But first I wanted to show the gray level, say the traditional ways of finding the textures. And that was end of today.